All right, welcome to CS 3510. This is lecture L02A, and the topic is arithmetic. Why are we doing this? Really, cool thing about number problems is there's just lots of cool questions you can ask about numbers. So it gives us lots of examples of divide and conquer algorithms, opportunities for us to understand how to do recursive programming, and opportunities for us to apply the master theorem and so on, right? Arithmetic is an old-timey fancy word that just basically means things you can do to numbers. What can you do to numbers? You can add them, you can multiply them, you can divide them, you can take GCDs, you can do exponentiation, all this kind of stuff. And that's basically what today's, at least the first half of the lecture is going to be like. Many of you come in with this idea of only doing something what's called fixed point arithmetic. And fixed point arithmetic is not like incorrect or anything, but it just basically means like addition and multiplication take constant time. And then in some larger problem, you're concerned with how many multiplications or how many additions am I doing. And that's totally fine in most contexts, but not specifically in this lecture. But it will be for most other lectures, including the one when we come back from the break. The other, the way we measure a number is a constant number of numbers. Two, and then we measure the time and the size of the number. So, for example, you have been told like addition is constant time, and multiplication is constant time, and that's true if the number is less than 32 bits, because you ask Intel very nicely, here's my two numbers, please add them. It calls the add instruction, and then it writes that number down somewhere, and then you read that, and that sounds like constant time. But the problem is that a 32-bit adder cannot add 34-bit numbers, and so on, right? So what if you have a number that's 1 trillion digits long? What happens is you have to store this number in a sequence of 32-bit registers. 32 bits here, 32 bits here, 32 bits here, and then they're chained together. When you add, you have to carry forward and so on. So a trillion divided by 32 is still like a trillion. So having a 32-bit or a 64-bit computer, having a larger adder doesn't really help. It just speeds things up by a constant factor, but that's when you consider asymptotically as the number of the size of your number, it doesn't really matter. So we, specifically in the arithmetic lecture, will consider numbers of an arbitrary size. Now the next thing we have to talk about is how do you represent a number? There are multiple different ways. Some are better than others. What's one way we represent numbers? Decimal, okay? So 17 would look like that, okay? What's another way we can represent numbers?
Binary.
Yeah, binary. 16, 8, 4, 2, 1, okay? Those are both two representations of the same object. We don't care about the representation, we care about the object. But we got to represent things somehow so we can talk about them, right? The computer doesn't deal with an abstract mental thing. It has an actual, somehow has to deal with the object in some way. Now, which one of these is better? That one is shorter, so maybe it's faster. But if you have a number in decimal, how many digits does it take to represent that number? Let's say x is in base 10. X in base 10 takes how many digits? Yeah.
0, 9.
Yes. Okay. Let's say x is a specific number. It does take 10 digits. Sorry. How many digits is x? How many spaces do you need?
X over 10.
X over 10? Not quite. It'll end up being something like that later, but log 10 of x, right? Similarly, if x is in base 2, it takes log 2 spaces, right? So here's the number of bits it takes, here's the number of digits it takes, right? But is one faster than the other? Is one significantly smaller than the other or preferable than the other for us to do the arithmetic in, right? If you have, and this is, for numbers there's like canonical forms where it's like the problem is solved. But this is not, how do you represent the object is not a solved question in other situations. As we'll see in graphs, there's a matrix form, and then there's like a array list form, and so on. And there are trade-offs. You even know linked list versus array list kind of stuff, right? So there's trade-offs depending on how you represent an object. But here, is there a trade-off at all? Do you guys know the basis conversion formula? Let's suppose we wanted to convert log base 2 into log 10. Do you guys remember what the formula was? That'll be the other way. Let's suppose I'm just doing a basis conversion. Not quite. It is a fraction. There's some logs in there, yeah. I'll tell you, it's the log base 10 of x on the top, and then there's a log base 10 of 2 on the bottom. Something like that, right? For you can change a base any log except 1. Like you can go from log base 2 to log base 10 using this change of base formula, right? But notice that that's actually what? That's just 1 over log base 10 of 2 times log base 10 of x. Right? This thing is just a constant. So what we see then is that log base 2 of x is just a constant times log base 10 of x. And this is true for 2 or 10, 3 or 7, 17 and a trillion. It doesn't really matter because we see that log base 2 of x, O of log base 2 of x is equal to O of log base 10 of x, which is equal to O of ln of x, and so on. So we don't actually, when the log, quote unquote, is on the ground, we don't forget to write the subscript because we're lazy. We don't write the subscript also because we're lazy, but because it doesn't matter. Right? No matter what base you represent the number in, it's still under asymptotically the same size. The same number in base 10 or base 2 or any other base takes asymptotically the same size. The only difference between what base you represent it is what's constant you scale it by. Right? Now, rather than think about, okay, it takes log bits to write a number x, log of x to write that number, we go the other way. If we have n bits, so instead of thinking we have a number x, how many bits does it take to write down the number? Suppose I have n bits. What possible numbers can I represent? What is the largest number I can represent with n bits? It's 2 to the n something. Yeah, it's 2 to the n minus 1. What's the smallest number I can represent with n bits?
2 to the n minus 1 minus 1?
0.
Wait, say that again?
Sorry, not the smallest size, but what is the least number I can represent with? It's going to be 0, yeah. So with n bits, I can represent a number in this range. So we're not going to measure runtimes of algorithms as a function of n, but a function of the bits of the number, which is, n is not the number. N is the size of the number. N is going to be the number of bits of the number, which could be perhaps an exponentially large number in this case, right? Right. Questions on representations of numbers? Yes?
Can't you represent like numbers, instead of representing 0 all the way up to n, 2 to the n, can't you just represent any subset of numbers?
It depends on the cardinality of the set of numbers you want to represent. For example, given only n bits, I claim you could not write down the number 2 to the n plus 7 using only n bits.
Well, I would assign that number to all zeros.
So there is a whole theory of something called Kolmogorov complexity, where it's like what numbers could be quote unquote compressed. But when you have information in a compressed state, you can't really like do algorithms on it. Imagine you have every data structure as a zip file. Anytime you wanted to work on it, you would just unzip it and then do your algorithm and zip it again. But what if that zipping and unzipping is slow? So that doesn't really like help us sometimes. It's just like technically it saves storage space, but then the algorithms are all kind of worse for this reason, right? So usually we choose a form, not that's the smallest to represent the number, but is the fastest for algorithms to work on quickly. For example, you could also represent a number by its prime factorization, right? Every number has unique prime factorization. Just store the prime factorizations. And in fact, don't even store those as bits. Store the prime factorizations of the prime factorizations and so on. Then you can factor any number really quickly, but you couldn't like add 2 numbers. It would be exponential time to add 2 numbers, which is like kind of useless, right? So it doesn't really help us there. Yes. That's like a programming thing. They're like, what is the difference between a negative number and a positive number? There's a bit in the front that's like a 1 or a 0, right? Signed or unsigned numbers, so it's just kind of like, it's fine. Same things. Usually, just for simplicity, we stick to the positive numbers, and then we just say like, oh, asymptotically, everything's the same if it was negative, right? Leave it as an exercise kind of thing. So, good question. More questions on representations of numbers? By the way, do you know why we use base 10? You have 10 fingers, you know, so like the computer uses base 2 because it's got a signal or no signal. It's 1 or 0, right? We only reason as a culture we use base 10 is because we have 10 fingers, right? Again, the choice is arbitrary though. And an alien with 8 fingers or whatever could still do the same math. They would just do everything in base 8 and it would be asymptotically the same speed. Okay? All right, we need to do things to numbers. What's the simplest thing you can think of doing to a number? That takes constant time, yes. There's a second. What's the second simplest thing you can think of doing to a number? Adding numbers. So we're going to add two numbers. Addition. So let's consider addition of two numbers. Let's just take two numbers in binary. Let's think of the grade school way, the way we all learned how to do it. Instead of base 10, you know, everyone knows how to add two pretty long numbers. And instead of base 10, we're going to just do base 2. It's the same algorithm. 1 1 0 1 1 0 0 0 1 1 0, and then we'll do, I don't know, 0 0 0 1 1 1 1 1 0 1 1. Okay. And let's add those. So how do you add numbers? You look at it, you write down a 1 or a 0, and then if it's a 3, you carry, right? So 0 plus 0 is 0. 1 plus 0 is 1. 1 plus 0 is 1. 1 plus 0 is 1. Actually, this was not a good choice. Let me do some carries in there. Okay. 1 plus 1 is 2. So what we do is we write down a 0, and then we carry the 1. And then we did 1 plus 1 is 2, so we write down a 0, and we carry the 1. And then 1 plus 1 plus 1 is 3, so we write down a 1, and we carry the 1. And then we have 1 plus 1 plus 1, which is 3, so we write down a 1, and we carry the 1. And 1 plus 1 plus 1 is 3. So we write down a 1 and we carry the 1. And 1 plus 0 is 1. 1 plus 1 is 2, so we write down a 0, we carry a 1. 1 plus 1 plus 1 is 3, so 1, 1. Okay, now that's probably right. How long did that take?
Like 30, 40 seconds.
Yeah, sure, number of steps. As a function of n. It was pretty fast, though. I couldn't multiply numbers that big or factor them that quick, so it certainly didn't take. It appears fast, right? Let's suppose both these numbers were n digits, n bits, yeah. L of n. Why?
Because you looked at each digit.
Yeah, that took at most 3 steps with a carry. At most 3 steps. At most 3 steps. At most 3 steps. And then maybe I have to write down an extra bit here. So that's like something less than 3n plus 1, right? So this takes O of n time. Okay, linear time to add two binary numbers. By the asymptotic stuff we just said, if you were to add two decimal numbers, it takes the same time. Okay, can you do it any faster?
I doubt it,
Why not, though?
because you'd have to read the inputs.
Yeah, it takes at least n time to read the input. So in fact, this is our first algorithm that has perfect, like it's completely solved. You know, we don't have to think about anything else. It's just, it's done for us, right? But here's sort of the argument about why most algorithms have, by this algorithm it has a linear time upper bound. But by an argument we'll do in a second, it also has a linear time lower bound. And basically the idea is like you need to read the whole input to do it correctly. Almost every algorithm you can think of should have a linear time lower bound. The exception is binary search, or things that are like binary search, right? Here's sort of the idea behind the argument. Assume to the contrary, it reads at most n minus 1, it takes at most n minus 1 steps. Then some bit is not read. Take any input, some bit is not read. Let's suppose it's this one, right? It doesn't read that single bit, right? Now, no matter what that bit is, the computation path is the same. So give it two different inputs, one where it is a 1 and one where it is a 0. The answer should change, but the algorithm's computation will not. So it'll give the same answer when it's supposed to give two different answers. That's a contradiction. The algorithm is incorrect. So because it didn't read that bit, it couldn't correctly solve the problem. Therefore, it must take at least linear n steps, right? Done. It doesn't need to be in that much detail, but most of the time you can say, obviously, I need to read the whole thing to do it correctly. So QED. Addition is done. Questions on addition? Okay, what's the third simplest operation you can think of on numbers? Subtraction, yeah, that's going to be what's the time complexity of subtraction? It's going to be addition of a negative number, yeah. So you throw the one bit in there, you do a little bit of parity checking, and then you add those two together, right? So subtraction would also be linear time. What's the fourth simplest operation we can think of on numbers? Multiplication, which is what we're going to spend the majority of today's lecture on, actually. So the first way you learn multiplication is how? Like, what's the simplest grade school way? Sorry, what? Long multiplication? What is that where you? This table thing? Okay. Yes? Yeah. So I think that's the same thing. I think we all call it slightly different things. But suppose I have numbers 1, 1. I'll do it over here. I have 1, 1, 0, 1, and let's say I have 1, 0, 1, 1, and I want to multiply these together. What I'm going to do here is you take this bottom, each digit here, you multiply it by this, and then you write it down. And then for each one, you shift it over some. So what's that going to be? That's going to be 1, 0, 1, 1. That's a 1. So I'm going to do 1, 0, 1, 1. That's a 0. 0, 0, 0, 0. That's a 1. 1, 0, 1, 1. Okay. Now when I add all those, what is that going to be? 1, 1, 1. 1, carry the 1. 1 plus 1 is 2, which is a 0, carry the 1. 1 plus 1 is 2, which is a 0, carry the 1. 1 plus 1 is 0, which is a 2, carry the 1, which is 1. Okay. Now that's probably right. Okay, so that's the grade school multiplication. We all did this. This is just review, kindergarten, right? First thing, what's the time this takes? Why?
Because you have to, for each number, you have to check the other number, like, I don't know.
It just feels like n squared is pretty good intuition, but in order to get graded in things, right, you would need to explain why. Yeah.
You have to multiply each bit from the bottom number with each bit from the top number.
Oh, almost. So if you had to multiply each bit from the bottom number by each bit from the top number, I'll tell you a story 3 algorithms from now about that idea. Hold on to that idea. But why is this run in n squared? Yes?
You iterate each digit for the top, but then you write however many times. Like
Yeah.
however many digits are up there for the bottom bit multiple times.
Exactly. So this is n numbers here, and we have n numbers, one for each bit. So we do n minus 1 additions. You add this number to this one, to this one, to this one. So you do n minus 1 additions of n-bit numbers. That's like O of n plus O of n plus O of n n times, which is going to give you O of n squared. Okay. So not like incredibly slow, but not particularly amazing or fast. By the way, why is this correct? You were taught this, but do you know why it works? Let's take it 5 seconds to do a correctness argument. If this was, let's call this top number x, and let's call this bottom number y. And then let's say that y as a sequence of bits is equal to yn y2, y1, right? So all we want to do is make a quick argument that the algorithm that is outputted by this thing is actually the product that we expect it to be. So what is actually outputted, though, is not just x times y, because we don't really know that. It's just the sum. So let's just write the sum out. It's going to be x times y n 2 to the n minus 1 plus x times y, let's say 3 to 2 squared plus x times y2 times 2 plus x times y1, right? That's what's actually outputted by the algorithm, right? Let's undistribute this, and these bits, by the way, yi is either a 0 or a 1, right? And when you're doing base 10 though, it could be a 3 or a 4 or 5 or whatever, right? Let's undistribute an x. We get x times yn 2 to the n minus 1 plus y3 2 squared plus y2 2 plus y1, right? What is this? Yeah, this is y. So this whole thing is just x times y. So it does actually output the correct answer, right? Probably never seen that before, even though you've known this algorithm since grade school. This one is quadratic time, right? Questions on that? That's sort of how a correctness argument has to go. You don't always need a correctness argument, but basically it's like, why is the output of the algorithm actually what I think it's going to be? And basically you would argue, why is the sum of stuff the actual thing that I'm looking for? You do a little bit of math, you get your x times y at the end, you know, QED. Okay? This is not the only, any questions on this algorithm? Right, we know this. This is not the only multiplication algorithm, by the way. There's a famous one found by Al-Khwarizmi. This one's only 1,000 years old. And it is a recursive algorithm. Let's say we want to multiply x and y. Every recursive algorithm, of course, needs a base case. We say, what should our base case be? If y is equal to 0, return 0. Y, 0 times anything is going to be 0. Else we're going to return, we're going to have z be on a recursive call of mult of x and then the floor of y over 2. Now what is the floor of y over 2? It's just rounding down. The floor function rounds down, we divide y by 2 and then we round down. In a computer science way, what's an easy way to take an n-bit number and compute the floor of y over 2? Bit shift. This is also just y. I think that notation is correct, right? So that's all that is. And then what we're going to say is if y is even, return 2 times z. If y is odd, return 2 times z plus x. Okay, that's it. That's the whole algorithm. Two things. First off, why does this work? We want to argue about the correctness, and then we'll make an argument about the runtime. So correctness. Why does this algorithm work? It's almost ridiculous that this is what divide and conquer algorithms look like, because it's almost obviously correct. We'll proceed by induction. Base case, y is equal to 0. We're good. Y, anything times 0 is 0. Now suppose by strong induction that z is actually equal to this. So we have two cases. Case 1, if y is even, then we want to argue that 2 times z is actually x times y. So 2z is equal to 2 times x times y over 2, which is equal to just xy. Almost ridiculous. It's almost like, it doesn't feel like there's a real algorithm here. And that's kind of what makes divide and conquer both a little frustrating to like implement and also understand, but it's also like ridiculously simple. There's a quote by a guy, he's like, proof by induction kind of feels like cheating, because you already get the answer and then you just have to say that's what the answer is. You just take x and y over 2 and you multiply those together by the magic recursion, and then you multiply that answer by 2, and obviously that's going to give you x times y, because you asked recursively what is x times y over 2, and then you multiply that by 2. So of course the 2's are going to cancel out, right? So in the case that y is even, it's simply that easy, right? Case 2, y is odd, then 2z plus x is equal to 2 times, what is the recursive call returning if y is odd? What is the floor of y over 2 if you know that y is odd? 3, the floor of 3 divided by 2 would be 1. So that'd be odd?
Y minus 1 over 2.
Yeah, it's going to be x times y minus 1 over 2 plus x, right? Then we're just going to x times y minus 1 plus x. xy minus x plus x, xy. Easy. Correctness, the algorithm is correct. Questions? What's the runtime of this algorithm? So there is no master theorem we can really apply here, but how many, when you don't have that, what you really do is kind of like measure the number of recursive calls and then consider the maximum work done at each recursive level, right? So how many recursive calls are there? Yes?
Log y.
Log y, but y is a number that takes n bits.
Log n.
N. And this is not like a incorrect thing. It's just a convention that we'll enforce. If y takes n bits, every time you shift off a bit, that takes one recursive call. So the recursion depth is actually n. But in terms of, it takes n is equal to log y. So instead of saying log y, we'll say n. Yes. So we have n recursive calls. How much work is what is the maximum amount of work done at each recursive call?
Yes.
M, because if y is odd, then you have to do the addition.
Yes. In the worst case, you have to do an addition. So what's the runtime of such an algorithm?
Thanks, Ray.
Yeah. So asymptotically, at least, this algorithm does not actually speed anything up. We have done a second divide and conquer algorithm so a second algorithm, this one is a divide and conquer algorithm for multiplication, but it's not any faster. It's the same asymptotic runtime. Questions on that algorithm? Again, what is the two things we did here is the runtime and then the correctness. So, all right, let's try again. Let's do a third algorithm. Instead of splitting recursive calls of x and y into bits at a time, let's just try and split the bits in half. So let's say x is going to be equal to, let's say, like xl, sorry, hold on. Yeah, so let's say x is going to be split its bits as if it was an array into two halves, which is xl and xr, and then y will split as well into yl and then yr, right? So what this means here is that these are two numbers, these are four numbers now, but it's the case that x is equal to 2 to the n over 2 xl plus xr, right? And then y is equal to 2 to the n over 2 yl plus yr, right? So n bits, xl and yl are how many bits each? Yeah. Yeah, each one's half as many bits. Just to give you an example, suppose we had 1, 0, 1, 1, 1, 1, 0, 0, something like this, okay? What you're going to do is take this as two numbers that look like that. You're just going to chop it up into two pieces, okay? Why do we care about this? Well, let's factor in FOIL. X times y is then equal to 2 to the n over 2, xl plus xr, 2 to the n over 2, xl plus, yl plus yr. And then we can factor in FOIL, and then we have a couple subproblems. So we're going to get 2 to the n xl yl plus 2 to the n over 2 xl yr plus 2 to the n over 2 xr yl plus xr yr. Right? And just to write that one more time, we're going to get 2 to the n xl yl plus 2 to the n over 2 xl yr plus xr yl plus xr yr. So here's the divide and conquer part. This is one top level n-bit multiplication, but we can represent it as a few multiplications, but each of these multiplications has at most n over 2 bits, right? So in fact, we have a divide and conquer recurrence here. what is our A, B, and D, right? How many recursive calls do we have? 4. What's the size of our subproblem? Yes. And what is the amount of work done? This is kind of, sorry, go ahead. Yeah, it's O of n, but why? It's a little open-ended, debatable, but it is O of n, but why? Yeah, well, we already have the 4 multiplications covered. Recall this step is supposed to be all the other stuff. It's supposed to be it's supposed to account for everything that's not the recursion, including the division, it's including the combination, right? So this would account for how long does it take to split x into xl and xr? How long does it take to do this multiplication? How long does it take to do this addition, right? How long does it take to split x into xl and yr, xl and xr? You want to split a number of bits into 2 halves. How long should that take? Not quite. What if n is a billion trillion digits? Can't take constant time. Yeah, but why? Yeah, you can do a couple bitwise operations. To get xr, for example, to get the right half you can mod. To get the upper half you can shift. So that both of those could take linear. How long does it take to multiply a number by 2 to the n? Yeah. Why isn't it n squared?
Because 2 to the n is constant.
It's not a constant. N is really big. A trillion, billion, gajillion digits. Yes. Shift again. Shift it n times. Shift, 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 shift. N shifts is going to be n steps, right? Think of this as appending. Now, in this special case, multiplication is fast because you're just appending n zeros to the end of it, right? How long does it take to add? Yeah, linear time. So linear, 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 that's like 3 linears. Do that some number of constant times. You're doing something like 3n work. So linear. Master theorem. What's A, B, and D? What's log base 2 of 4?
2.
Okay. And which is greater, 2 or log base 2 of 4 or D? Yeah. Right. So what's the runtime of this algorithm? Yeah, this is O of n squared. Essentially, you just compare these 2 numbers and take the bigger one. Because you know it's bigger or worst case. You just take whichever one of those bigger. Recall that in the summation, so 2 things about the master theorem. You both need to understand the proof of how it works, and you also just need to know how to apply it without thinking. So here I just memorize the thing, and I'm like, I just compare these 2 numbers, and then I choose the max of those 2. Except when they're equal, I throw a log on there. But if they're not equal, this is a 2, this is a 1. So I'm taking n squared. Okay, that's not better though. I have the same 3 algorithms now for multiplication. They're identical. Same runtime. This did not improve anything at all, right? Now, question before we get into the next algorithm. Questions on that algorithm? Yes.
Why is A4?
Y is what?
A4.
A is 4 because we have 1, 2, 3, and 4. So if I were to write the code, it would be, and I'll just be explicit, it would be mult of x, l, y, l, mult xl, yr, mult of xr, yl, and it would be mult of xr, yr. So the top level algorithm, were I to write out the code, would call it 4 times. Then it would do the linear time recombination to get back the actual x and y. Yeah. More questions on this version of multiplication? Yes?
What is the n over 2 representing it?
The n over 2 here?
Or the t n over 2?
Here? Right. Because we are doing 1 n-bit multiplication at the very top, we're representing it as the size of subproblems, right? So the b here is like how big is the smaller thing. Remember in merge sort, it's like half as many elements in the array, right? So here, xl and xr, yl and yr are half as many bits of x and y. So when you multiply, let's say, xl times yl, you're doing an n over 2 bits times n over 2 bits multiplication. And that's the size of the subproblem. So you're doing 4 smaller multiplications instead of 1 bigger one. Yeah. More questions on this one? So again, not faster. That's not very good. So a lot of multiplication was done this way. Like people kept trying. Once the theory of algorithms got the ball rolling, people kept trying to. Okay, let's try a different kind of multiplication. Can we beat it? Let's try a different kind of multiplication. Can we beat it? And there's actually a few more n squared time algorithms for multiplication that get seemingly more and more complicated, but don't appear to speed up the runtime at all, right? So the next question is, okay, is this it? Can you do any faster? And so people started to ask, is there a quadratic time lower bound on the number of bits, if n is the number of bits, of multiplication of two n-bit numbers, right? And it's a very feasible conjecture. If you had to guess, would you believe that there's an n squared time lower bound or not? Let's take a poll of the audience. If you think there is an n squared time lower bound, raise your hand. Okay. If you don't think there's an n squared time lower bound, raise your hand. Okay, why not? Yeah.
Because we're taking this class.
Yeah, I would have told you if it was the answer, right? So that's a good intuition. Have you guys heard the name Kolmogorov in any context? Actually, I just said it today earlier, Kolmogorov complexity. But Kolmogorov is this, like, he was a Soviet mathematician. He organized this large conference because he wanted to prove that there was an n squared time lower bound. And it is a seductive conjecture because you have n bits and you have n bits. And it appears that to do a multiplication, you have to check all possible pairs. And there's n squared pairs, right? N choose 2 is O of n squared. So it's like probably at least n squared. So he organized this conference. He got all this funding. It took a month of, the conference was a month. He had hotel accommodations for a month. He had lineups and lineups of people speaking. And then on the third day, an undergrad came up and found an algorithm that beat the n squared lower bound. It was O of n to the 1.59. So his name was Karatsuba. You may have heard his name. And basically, the conference was ended before it really began. There was nothing left. The whole point of the conference was just, what else are you supposed to do? This was only on day 3. So let's present Karatsuba's multiplication. It's not too hard. Basically, what he noticed here is if you take the same formulation that we have, what do we have? We have 2 to the n, xl, plus 2 to the n over 2, xl, plus xr, plus what is that? XL, So to get this middle term, it takes 2 multiplications. But he found a way you can actually do it simpler than this. Y, XL, YR plus XR, YL is actually equal to XL, YL plus XR, YR. Make sure I got this right. No. Sorry. XL plus Y, XR, YL plus YR, minus XL, minus XR, YR. Now, here's the reason that's important. This, naively, takes 2 multiplications. This looks like it takes 3 multiplications, but notice that we already have XL, YL, XR, YR. Those are 2 of the subproblems, so we've already computed this. So in fact, computing it this way does not take 2 multiplications. It actually takes only 1, which is this one. So let me write out the code of Karatsuba. XR. Let's just say we split it. That's done with shifting and modding and stuff, right? XYL, YR, split of Y. And then LL is going to take on the mult of XL and YL. RR is going to take on the mult of XR and YR. And then the middle will take on the mult of XL plus XR, YL plus YR, minus the lefts minus the rights, right? And then you're going to return 2 to the n LL plus 2 to the n over 2 MM plus RR. Pretend I put a base case in there. But that's basically Karatsuba multiplication, right? What's our runtime here? How many subproblems do I have? 3. I have 1 less now, actually. But it's come at a cost of additional work somewhere else. What's the size of my subproblem? It hasn't changed. It's still n over 2 bits, right? But the work done has changed. What's the work done now? So what's the work done? Splitting like this, mods and shifts, okay? That's linear time. Multiplication, that's the recursive call, we don't count that. We're just counting the conquering step, right? Base case, constant, whatever. These are set up fine. We have to do some additional additions here in order to set up the parameters for the stack or recursive frame call, right? So we do 2 more additions, and then we do 2 more subtractions of at most n bits, right? So we've increased the amount of work from like 3n-ish to like 7, 8n-ish, right? But that's just a constant. So in fact, this is still O of n work, right? So in fact, by increasing the amount of work done from like approximately 3n to approximately 7n, you can reduce a equals 4 to a equals 3, right? So you've increased the amount of work done, not enough to make a difference. And in fact, you could even increase this to like n to the 1.1 or something if you wanted. It wouldn't change the answer. But you can increase the amount of work done to decrease an entire recursive call. So using this, he was able to save a whole recursive call. And let's do the analysis. What's a log base 2 of 3? Actually, you shouldn't know this one. It's like 1.59, approximately, right? And then d is equal to what? It's still 1. So we take the case of the winner here. So it's going to be approximately O of n to the 1.59, which is, again, this is O of n to the log base 2 of 3, right? So the next question, any questions on Karatsuba multiplication? The correctness follows the same. The analysis follows similarly. Yes?
So there's one multiplication. Which multiplication is that?
Right. So this is the old school way. This is the way all the way on that board, right? Which takes 2 multiplications. 1, 2. This is the new way. And it appears to take 3 multiplications. 1, 2, 3, right? The product of those sums. But here's the thing. You don't have to double compute those. You already have those. You need those anyway. So you compute those for here and here, right? When you return them here and here. You already have those. So you only need to compute this multiplication right there. That's how you go from 2 multiplications to 1 multiplication. That's why we go from a equals 4 to a equals 3. By doing more work, we can set things up nicer so we have reduced an entire recursive call. And again, reducing a is a pretty good strategy for reducing the runtime of your algorithm because it affects the tree exponentially, right? Instead of having a branching factor of 4, a quartic-ary tree, you now have a trinary tree, which is of course going to be smaller, right? Pretty good. Questions on the analysis or the correctness of Karatsuba? The next question is, can you prove this? Can you improve upon this? Can you make this any better? Can you change anything? Yeah, it's kind of still an open problem. So like, what would you conjecture a lower bound on multiplication to be? Give me any lower bound on multiplication. It takes n, n is the easy one. Let's do n first. Why is there a lower bound of multiplication of n bits? You got to read every bit. If you don't read every bit, you made a mistake, okay? You don't have to read every possible pair of bits, but you need to read at least every bit, right? Okay? Is there a better lower bound? Someone said n log n. Why?
This is a divide and conquer, so our lower bound has to be n log n.
Not quite. You could divide and conquer. Binary search had a divide and conquer lower bound of log of n, yes. So sorting specifically has an n log n lower bound. I thought that so two wrongs do make a right. There is thought to be a n log n lower bound for incredibly complex reasons that I don't even actually know. But there's some like conjecture something does something else. And then in like 2020, somebody actually found a very, very complicated algorithm that does multiplication in n log n. By the way, so like you do more linear work, you save a subproblem. Okay, fine. What if you split x and y not into lefts and rights, but let's say you split each one into like 6 parts. And then instead of 46 subproblems, you were able to get it down to like 42. Something like this. This kind of work has been done, and it's called Tomb Cook. And you can get a little bit better than 1.59. You can get like 1.43, something like this, right? Somebody else figured out a way in like 2020 to do n log n. But the constants are so big, it's not, nobody cares, right? Anything else I could say about Kurotsuba? Yeah, that's it. Any more questions on Kurotsuba? Okay, so it took us that long to give like 3 or 4 algorithms for multiplication, and this is the best one. Question? Yes?
What's the base case?
Let's say y is 0, return 0.
What about if it's just 1? Then
When we split it, so that's the other thing about divide and conquer, we just can assume everything's nice and that there's no things to work out. That's why my pseudocode only is a few lines of code. But know that even in the split, let's say it was an odd number of bits. Maybe I have to pad it by the next power of 2 or something, or maybe I split like 5 bits into 3 bits and 2 bits, and then when I split recursively the 3 bits into 2 bits and 1 bits, it's fine. Implementation, we'll do the hard stuff and then leave the easy stuff to when you actually have to write the code, right? Solves problems. More questions? Okay, let's do 2 more quick algorithms. So the next 2 algorithms are, one is on modular exponentiation, which is pretty useful in like cryptography and things. We mentioned the method of repeated squaring, but let's do a divide and conquer algorithm for modular exponentiation. And modular exponentiation, we want, let's say a, comma x, comma n. We want to return like a to the x mod n. Right? And each of these are n-bit numbers. The reason we do this is because like analyzing the runtime of algorithms like that write down really big numbers can be bad because the numbers can run away really big. And then you have like a really slow algorithm because it takes a long time just to write the number down, right? If the number is exponentially bigger, maybe it does take exponentially time to write it down. At least if we mod it by n, we know it's still of a certain size and we can use that in our estimation. But then you take this and then you can generalize to the case where it's not mod n, right? But let's suppose this is what we want to compute. It's not too hard. What we do is we sort of do recursion upon x. If x is equal to 0, what should we return? Yeah. Okay. Let's say z takes on a mod exp of a, and let's say x over 2, the floor of x over 2, and let's say n, right? If x is even, we're going to return, what should we return here? Almost. We have a z, right? It's a subproblem. I'll tell you, z times z. If x is odd, return a times z, right? Let's give the quick argument, the proof of correctness. Base case, we're good. Let's assume our induction hypothesis that the recursive call returns the answer correctly. Then we're going to have, if x is even, then we know that z times z is equal to, and this is supposed to be mod n, right? This is going to be a to the x over 2 squared, which is a to the x mod n. Easy. If x is odd, then a times z is equal to, what is z if x is odd? Correct? Okay. Run. What's the runtime of this algorithm? How many? So we're not doing a master theorem thing again. We're doing a sequential recursive algorithm. How many recursive calls are there? Yes.
N?
Yes. Suppose that the number of bits of x is n. Then we have O of n recursive calls. And how much work is done at each level? Yeah. Or y n squared. Yeah, so let's give two bad answers. Let's suppose there's n squared work done at each level. What's the total runtime of the algorithm? Yeah. Suppose we did Kurotuba multiplication at each level. What's the runtime of the algorithm? Yeah, so like in general, and this is a convention thing, it is true that multiplication can be done in 1 to the 1.59 time. But when you do the analysis, and you're considering bitwise multiplication, and you're doing multiplication of the number of bits, it's really ugly. So we just like kind of ignore it, and we just leave everything nicely, right? If an algorithm does run in n to the 2.59 time, it technically is still correct that it's n cubed time by properties of big O. So we would rather write this one than that one, because this is ugly. Because imagine you need this in something else. Imagine you have an algorithm that needs modular exponentiation, and that algorithm needs something, and things just get ugly really quickly. So we'd rather just do this one. We'd rather say modular exponentiation can be done in cubic time. That's much better than just normal exponentiation, simply because, not because it takes a long time to do the computation, but it takes a long time to write things down. So, questions on modular exponentiation? I'll give you one more algorithm, and then for this one, you guys maybe don't write anything down, because it's going to be a lot of symbols, and it's not particularly, well, I guess you could write some stuff down, but. Suppose we want to do matrix multiplication. Let A comma B be n by n matrices. And let's suppose we're working in a fixed point arithmetic. That means add and mult are O of 1. So we don't concern ourselves, we're not trying to concern ourselves with the time it takes to add or multiply the elements of those two. We're trying to concern ourselves with the number of such operations. So suppose every element of the matrix is MATLAB style. It's all 32 bits, something like this, right? There's some precision issues, or it's fine, who cares? Let's just concern ourselves with this algorithm as the size of the matrix grows, right? By the way, we're going to measure things as the dimension, which is n, but the input is actually 2n squared, because a matrix that's n by n has n elements, right? And we have two of them, right? So suppose we want to compute A times B. You know how to do this with Gaussian elimination, right? How do you do it? Yeah, you do that thing, right? And so. Well, you take that column, that row, bing, bang, boom, and then you write down a single element here, right? This is the classic pen and paper matrix multiplication method. What is the runtime of such a method? And to the fourth, it's a little faster than that. First off, how many elements are in the answer? Yeah, there's n squared things we have to write down. We have to actually compute n squared numbers. So we have n squared cells. Now, how long does it take to write down an element of the cell? Yes? 2n, let's just say n, yeah. You do an add and a multiply. This is a dot product, right? So there's an add and a multiply and an add and a multiply and an add and a multiply, but there's a linear amount of them, and that is 2n of them, right? n minus 1 additions, n multiplications, let's just say O of n. So it takes O of n work, not work, but like operations. We're counting the number of operations for each thing. So in total, this takes n cubed time, right? So the trivial way of matrix multiplication takes n cubed. Not too bad considering the matrices are already just n squared. But can we improve this? So let's try a divide and conquer approach. So suppose that A and B are equal into block form like this. So the matrices are a power of 2, and you can cut them in half and cut them in half, and then you get 4 smaller matrices, each of size n over 2, right? And then we could say that through properties of matrix multiplication that A times B would be the product of these two, and if we were to work it out, it would just be something like A11, B11 plus A12, B21. This is the part you don't have to write down. B11 plus A22, B21. And then this quarter would be A11, B12 plus A12, B22. And then this one would be A21, B1, A21, B12, A22, and then B22, okay? So if we were to write the matrices out, you can represent the block matrices this way. This gets dot product with there, and that this is the first quarter of the product matrix, right? But this is our divide and conquer recurrence. Notice that the dimension, you have n by n matrices. What is the dimension of each of these quarters? It's n over 2, yeah. They have a fourth of the elements, but the dimension is n over 2. So each of these subproblems is going to be size n over 2. How many of them do we have?
8.
Yeah. 1, 2, 3, 4, 5, 6, 7, 8. Nothing is saved. We have 8 of those subproblems. What's the work done at each level? Why is it n squared? It is n squared. Yeah. Why is it n squared? Oh, okay. Yeah. Sure, the multiplications are done by the recursion, though. So everything else would go into this conquer term. Why does everything else cost us n squared? Yeah.
Because when you do the addition, you have to do n squared additions on it.
Exactly. The addition of two matrices is defined as the addition of the elements. So this is n over 2 squared additions, n over 2 squared additions. So you're doing n squared additions, basically, 4 times. Okay? Quick, what's log base 2 of 3? Sorry. 8.
3.
Yeah, 3. Okay, my bad. D is equal to? Which one wins?
3.
Yeah. So this takes n to the n cubed. Okay. The trivial way took n cubed. The divide and conquer way took n cubed. So we didn't actually improve anything. I'll show you one more algorithm for matrix multiplication, and again, you don't have to write this down. There's this guy named Strassen. He's still alive. He still writes things. In the 60s, he figured out a different way to do the divide and conquer recurrence. And what he did was he said, don't write this down, but he called M1, let's say A11 plus A22, B11 plus B22, M2, A21 plus A22, B11, M3 takes on A11, B12 minus B22, M4 takes on A22, B21 minus B11. Okay, I'm getting lazy. Let's just pretend that there's a couple more. And then he read, so there's some things here. Each of those also takes one multiplication. But then he said that A times B is then equal to, of these matrices, M1 plus M4 minus M5 plus M7. This bottom one is M2 plus M4. This one is M3 plus M5. This one is M1 minus M2 plus M3 plus M6. Right? So something completely like arbitrary. It doesn't really like, how would you come up with this? And why do we care about this? We have a divide and conquer recurrence again. What's our number of recursive calls? We have 7 matrices we're doing this time. We're only doing 7 multiplications. The work done at each level is still the same size. And what's the work to recombine? It's still addition, so it's just n squared of them. By the master theorem, what is log base 2 of 7? It's less than 3. I think it's 2.81. D is equal to 2, so we see that this one wins. So this beats Gaussian elimination pretty quick. Not pretty quick, it's slightly faster. Now in practice, this is actually a terrible algorithm because you need to assume that the matrix is a power of 2. The dimension of the matrix is a power of 2. And if it's not a power of 2, you have to pad up to the next power of 2. And that is not cubic time. That's really, really bad. So this algorithm, in theory, works great. It beats matrix multiplication. Now, the current research is like, how fast is matrix multiplication? We don't really know. Nobody knows how to do these subproblems. There was an article about 2 years ago that figured out, like, in the special case of these Strassen-style divide and conquer stuff, if it was like a 4 to the n thing, an AI found a solution with like 55 subproblems for a very specific kind of matrix that could do, the AI actually discovered an algorithm that was beating what the current literature was on a very specific case of matrices. And then the next day, somebody else took the AI's answer and improved it from 55 subproblems to 54, something like this. So the humans now still hold the record, technically. Yeah, I'll just, one last thing, the current record is like n to the 2.3187, and then in like 70 pages, people figuring out all complicated stuff, they were able to improve this to this. So we're not making much progress in this area. It's a lot of work for little gain, and the constants are so large that you couldn't even fit the constants on a computer. But it's an interesting area of work, and it's interesting things that are being done. So let's take a break.